Okay, so an impulse question. So we've got a car travels at a constant velocity of 3 meters per second. We've got a car traveling at a constant velocity of 31 meters per second. When the driver notices a stationary truck in front of him, he applies the brakes to slow down at a constant rate. The driver is alert. The reaction time is 0.677 seconds. Okay, so A says, how far does he drive before the driver applies the brakes? Well, he goes 31 meters per second for 0.67 seconds, which is how long it takes for him to hit the brakes. So we know that velocity is meters per second, right? Meters per second. So we can say V is equal to displacement over time, okay, which is, they'll often use S as displacement. You know that is in meters. So just don't get confused. That's not seconds. And this is, so we want the meters, how far he traveled. So S is equal to V times T, which is equal to 31 times 0.677. Okay. And we get 20.99. Okay, now B says the mass of a car is 600, the mass of the car is 600 kilograms. And the time taken for the car to come to rest is 6.45 seconds. The T is equal to 6.45 seconds. Okay. Use the impulse momentum theorem to determine the force required to stop the car. So we know that impulse is equal to force times change in time. Impulse is force over the time. Remember, impulse with a cricket bat, the longer the time spent, the ball spends on the bat, the greater the impulse, the further it travels. So we've got the time, we've got the force, so we know that they want the momentum, they want us to use momentum. So that's, we know that impulse is equal to change in momentum. So we actually need to use that. So, well, the momentum of the car, okay. So when we say that momentum is always conserved, what happened in this situation is that the momentum was just transferred. So if you think of the momentum on the system, it was just the brakes was what changed the momentum. So there were the brakes that were acting in opposition to the car. So it's still the system.
Yeah.
In a way, what you can think of is like it's like it's hitting a wall. So when a car hits the wall, the wall pushes back to stop the car. So what we want to do is we actually just want to look at the change in momentum of the car, which is 600. So remember, P equals mass times velocity times 31. Change momentum. And so we'll just draw the car in here. Trying to find my trying to find the thing to draw. Oh, there it is. Okay. So we'll find the change in momentum of the car. Okay, so that's 31, which is equal to 600 times that's 1,186 0 0. Okay, because 31 times 6 is 186, and we put those two zeros on there. Okay, so that's the change in momentum, which is kgs per meter per second, which we know is the same units as momentum, as impulse. We did that in that first video that we recorded. So we can put that in because now we know the impulse. What do they want? So now we know the impulse is 18600. Okay, so let's just put, that was in red. So this was the answer in red. This is the impulse. So we can put that in here. We know the change in time. We'll put the force in pink. The force is what we require. And then the change in time is 6,45. And so the force is equal to 18,600 divided by 18,600 over 4,45. Let's put that in the calculator quickly. Clear. 18,600 one too many. Divided by 4.45 equals, and we get 4179. Oh, 6,45. 18,600 divided by 6.45 equals 288.372 newtons. Okay, so we see there the relationship between impulse and momentum. So the change in momentum tells us the impulse, which we can then use to work out the force applied by the brakes. Second question says design a poster about safety. So we can leave that. Yeah, but just from a theory point of view, the longer the further you are away from the car in front, the longer you have to stop. Which means you can this time, the 6,45 can be spread out longer, and so there's less of a force, because as soon as you collide with that car in front, you have that force.
Yeah.
And so the smaller the time, if the impulse is the same, the smaller the time, the greater the force. Because we know that this car, if it's coming to a stop, this is the change in momentum, this 18,600. So if that's coming to a stop, the force required is based on how long it takes to stop. So if this change in t is tiny, in like a head-on collision, the force experienced by those people in the car is deadly. Whereas if you have more time to stop, obviously there's a less of a force, and it's obviously going to be much safer. These crumple zones in the cars are all about changing the time that it takes to stop. So you've got the crumple zone. So instead of being stopped here, you're crumpling up. And so you're just trying to extend that time that it takes to accelerate to zero, lessening the impact. So yeah, that's impulse. So should we try and